Okay, so we're in our notes here, and I just wanted to recap what we were sort of hurrying through at the end of last class, which is this notion of talking about horizontal asymptotes. And so I just want to point out that the horizontal asymptotes are a feature of the exponential functions that we can talk about in a more formal way. So if we go ahead and just look up earlier in the notes at these graphs right here, we can do some examples. So if I'm looking at this graph 1, I notice that if I was trying to describe this asymptote in casual language, I would say as we move towards the left, the graph gets closer and closer to 0 but never approaches it. So that's a very wordy way of trying to say something that has a more technical meaning. And so mathematicians, we like things very technical, right? So the expression we would say to talk about that behavior is we would just write that the limit as x goes to negative infinity of whatever letter this was, let's just call it f of x, that is equal to 0. So sorry that's highlighting there, but so that's just a way of sort of formalizing the fact that as we move towards the left, as x goes towards negative infinity, the function is approaching 0. And we could say the exact same statement about this graph number 2 and graph number 4. And the interesting statement with these three graphs here, graph 3, 5, and 6, would be to say that the limit as x approaches positive infinity of the function is equal to infinity. So that's what I was trying to talk about at the end of class there with the notation. Let me also just, since I sort of skipped over number 8, let's talk about that. If I were to graph f and I'm just sketching it, now I told you that I'm not going to actually have you sketch them, I'm going to have you do a matching, but I want you to just get a feel that you can sketch such things. If I was graphing f, I know that it would be, the parent function would be 3 to the x, which is an increasing function, increasing exponential function. And then there would be this 2 times it. So you might actually view f of x better as 2 times 3 to the x and then plus 5, so that you really saw it in this way as this is like my multiplier that makes a vertical stretch, and this is adding, this makes it go up 5 units. So instead of having my horizontal asymptote down at the x-axis, it would be up at x equals 5, I'm sorry, y equals 5. And then it would still have that same sort of shape as 3 to the x, but instead of so this vertical stretch, instead of this being the y-intercept in this case, since we've shifted it up 2, our y-intercept is also going to be up. I said shift up 2, I'm sorry, shift up 5. So our y-intercept is not going to be at 2, but instead it's going to be up at 7. So our y-intercept would be 0, 7. I know that's not the best handwriting, and that's a sketch. That's all I would be looking for. Versus g of x, I would be taking my 3 to the x function that's been vertically stretched by a factor of 2. So that would mean that originally it would have a y-intercept of 0, 2. But this x minus 5 would be shifting it to the right 5. So instead of having the y-intercept like here at 0, 2, that point gets shifted over 5. 1, 2, 3, 4, 5. So I'd have the point 5, 2. It's still going to have a horizontal asymptote at the x-axis, and it's still going to be exponentially increasing, so it's just going to sort of look like that. Again, sorry these graphs aren't perfect. This tablet, this is the best I can do. And then this last one would be taking, again, that 3 to the x, which is increasing with a y-intercept of 2, except this negative x. So inside the function, if you put a negative x inside the function, remember that that's going to reflect it. And we could see, I'm going to just scroll back up just to remind you where we have this information. Okay, so we have an inside the function, we have that reflects over the y-axis. So the 3 to the negative x, so we're picturing our regular 3 to the x function, which is normally increasing. But when we reflect it over that y-axis, what's going to happen is it's actually going to be decreasing. So sorry, I know this is taking a second here to get back down. Right, so it's going to still have that y-intercept at 2, 0, 2, but now it's going to be decreasing. And remember, the other way to have viewed this is to think of this as 2 times 3 to the negative 1 to the x. That's using properties of exponents. And that's the same thing as 2 times 1/3 to the x. And so now we see that that's a base value between 0 and 1. And so now it makes more sense to be decreasing. So we skipped over those, so now we have complete notes on that portion. We talked about the notation of the horizontal asymptote. Let's just finish up these last couple ones that we didn't get to. Given the graph of g of x equals 2 to the x plus 3, which is this one, notice that instead of the y-intercept being at 1, it's shifted up 3 units, so it's up at 4. It asks, what's the horizontal asymptote here? So instead of it being the x-axis, because of this plus 3, it's been shifted up 3 units, and so that's the equation y equals 3. Right? That's this line, like right here. And so write a statement about the graph above using limits. So we see that the place where we have our asymptote is happening down here at negative infinity. So we would write that the limit as x goes to negative infinity of, in this case our function is g of x. So as x goes to negative infinity, what's happening to our graph? Well, it's not approaching 0, it's actually approaching 3 in this case, right? Because that's the horizontal asymptote. So my asymptote is up at 3. And I'm going to stop this video here, and we'll continue in the next video with the next portion of the notes.